few things I wanted to say before we start today's lecture. And first off, I'm going to remind you all to hold your questions till the end so we can get the mics around and or online questions we can deal with. A few things that are coming up. Very shortly, those of you that need to do a 5-year renewal application will be receiving an email with all the information in it. That is going to be due April 1st. New membership is due March 1st, and letters went out to all the recent emeritus faculty that are not members already that the application is open and is due by March 1st. If you have friends that perhaps aren't paying attention to email from OSU, you might encourage them to take a look at our website and about our programs and apply, because of course we always welcome new members. Also, small grants will be due later in the spring, May 3rd. All this information is at our website, so please refer to that also, or send people there to take a look. There will also be email calls for people who want to nominate or perhaps nominate themselves to become a steering committee member next year. We need 3 new members. And also about lecture proposals for next year. So you'll be seeing emails about that through the spring, but you might think about it right now and start planning this great application. I have this wonderful lecture I want to give, etc. There you go. Okay, today's lecture is Professor Ron Salmon. He was awarded his PhD in math by Yale and joined the math department at OSU in 1975. He received the OSU Honors Service Award in 93, Distinguished Teaching Award in 97. In 2006, he received the Levi Kant Prize of the American Mathematical Society, AMS, for expository writing for an article, A Brief History of the Classification of the Finite Simple Groups. And in 2012, he shared the AMS Steele Prize for Mathematical Exposition for the book, The Classification of Finite Simple Groups. He mentions that he owes his writing ability to his mother. He has been a research collaborator for over 40 years with Richard Lyons and the late Daniel Gorenstein, both of Rutgers, on a series of volumes, 10 of which have now been published by the AMS. The 11th is in progress. He has greatly enjoyed teaching at Ohio State, especially in his special area of abstract algebra, for which he's written a textbook and has supervised 6 PhD students, 5 of whom have had fine careers as math faculty in researchers. His title today is Sporadic Simple Groups in the OSU Math Department. I thought it was a really catchy title. Ron, please, if you would.
Well, many thanks for the invitation and the opportunity to come, and it's delightful to see everyone on this beautiful day, and even more than half of you who are not my colleagues in the math department, so that's my talk title, and I feel like I owe you an explanation of some of the words. I assume I don't have to explain OSU Math Department, but the top line requires a little explanation, probably. So to begin with, the word group or group because it was actually introduced in French by a Frenchman around 1830, a Frenchman named Évariste de Galois. And a group is a collection of symmetries or rearrangements of an object or a collection of objects. It could be a reshuffling of a deck of cards, or it could be rotations of a three-dimensional sphere or a two-dimensional ring. And the important thing is, I wanted to mention a friend, Percy Diaconis, who's not a group theorist. He specializes in probability and statistics and such, but he's a big fan of group theory, which he uses quite a bit in his work, just to indicate that it does have applications outside of group theory itself. And Percy is an extraordinarily colorful person. I wouldn't want to be the person following him as a speaker because it's hard to follow Percy. He's incredibly charismatic. He dropped out of high school to join the circus, but is now a full professor for many years at Stanford University. Anyway, getting back to what a group is, the important property of a group, besides the fact that it's a set of permutations, is that we consider this set to be equipped with a multiplication. I mean, if you're a mathematician, you think of composition of functions. If you have two functions, f and g, f composed with g could be called the product of f and g. Or in general, if you do one rotation to this ball and then you do another rotation, then the final effect is equivalent to having done a single third rotation. And so you call the third rotation the product of the other two rotations. So there's a multiplication structure. It's a non-commutative multiplication structure. It's not like multiplying integers where 2 times 3 is the same as 3 times 2. In the context of groups, things are a little more subtle. The multiplication, the order in which you do these motions can lead to different results. If you do first one rotation, then rotation A, then rotation B can be different from rotation B followed by rotation A. But in any case, it is a multiplication structure, and the size of the number of permutations on a set grows rather rapidly. So if you're even just shuffling a set of 5 playing cards, there are 5 factorial, 5 times 4 times 3 times 2 times 1 different ways you can arrange those cards. So the total number of permutations of a set of just 5 things is already 120. And it keeps going up rapidly. 6 things is 720, 7 things is 5,040, and so on. And the set of all rearrangements or permutations of a set of 5 cards is called S5, or the symmetric group of degree 5. Symmetric because this is sort of thought of as symmetries. If you have a geometrical object and you turn it and it looks the same after the motion as it did before, then you say this is rather symmetric. If this were just a perfectly smooth sphere, there'd be infinitely many permutations you could do so that it looked exactly the same before and after you were done. So that would actually be a so-called infinite group of permutations. Because this is actually a sort of miniature soccer ball, there are these distinguished pentagons and hexagons on it, and you can only, so if you want to respect that, you want to ignore the label of the manufacturer, but if you want to respect the position, the fact that if you have a pentagon, an orange pentagon sitting on the top, then when you rotate it, you only consider it to be the same when there's another orange pentagon at the top. And there are 12 orange pentagons, so you can only possibly be doing 12 motions. And it turns out the total symmetry group of this figure, thought of as a soccer ball, not as a sphere, just is the same as this group, the symmetric group on 5 letters, at least if you permit reflections. If you only permit rotations, it's half that big, and it's the group that's called A5, or the alternating group on 5 letters, is the set of all rotational symmetries of a soccer ball. So the same group, thought of abstractly as a group, can play several roles, and that's fundamental to the importance of group theory in the rest of the world. I mean, you can think of a group as acting on various different things, and chemists will think of it as acting on a molecule and rotating a molecule about, or acting on a crystal structure and moving the crystal structure around. And it was very interesting in the 19th century, and I think continues, but beginning already in the mid-19th century, chemists were very interested in group theory in the context of symmetries of crystal structures. And subsequently, physicists became very interested in symmetry groups of the universe, a symmetry group of some structure. And so there are important applications for groups, to the fact that they can be thought of in different ways. Okay, group theory, in some sense, began with Joseph Louis Lagrange, who was in 1770 to 1771, was was the mathematician in residence at the court of Frederick the Great in Prussia. And he gave a year-long series, so far as I understand it, a year-long series of lectures in the year 1770 to 1771 on the problem of solvability of equations, looking for formulas like the quadratic formula that's used to find the solutions for a quadratic equation. Mathematicians were fascinated with the question of whether you could produce similar formulas for equations degree 3, 4, 5, and so on. And Lagrange did the first really deep study of this question and introduced the notion of permutations as applied to the roots of the solutions of this polynomial. He was interested in permuting the set of all solutions of this polynomial, and he thought of the action: if the polynomial had degree n, then it would have n roots, and so this symmetric group on n objects would be moving around these roots, and this is what Lagrange studied. Now, you can ask for certain subgroups of a group. So the set of all rotations of this sphere is a big group. If you ask for all the rotations that keep these two antipodal pentagons fixed, then you can only rotate it about that axis, and you have a smaller number of rotations, and that is a so-called subgroup of the full group. So if you have a set of permutations within a bigger group, which is itself closed under multiplication, so that if two things are in that set, their product is also in the set, then that's called the subgroup. And Lagrange proved the remarkable theorem that the size of any subgroup of a group must divide the size of the whole group, or at least he particularly proved it really for the symmetric group on n letters. And we managed to do this without knowing what a group was, or without knowing the definition of a group, but I could explain, but I won't try to explain how he could pull off that trick. So there was no notion of a group yet, but he did prove this theorem, which caught the imagination of a lot of mathematicians and made them to start thinking about these types of structures. And so a number of things were done between 1771 and the 1830, but the next enormous advance in the subject, absolutely unbelievable advance in the subject, was accomplished by a very young mathematician, Évariste Galois, who managed to be something of a political revolutionary, did got some free time to do his work by being put in prison by the French government for several months and having nothing else to do, and who tragically died before his 21st birthday. So if there were, it would say May 31st, 1832. In fact, if you've seen the musical Les Mis or read Les Miserables, there was this revolt against the government of the King Louis Philippe that's featured the battle on the barricades of Paris, and that happened almost exactly the day that Galois was shot in the duel. So, but in the short time that he had to live, he did an amazing thing. And the amazing thing is that he realized that groups are not just sets of things. It's not just a list of things, or not just even a list with a multiplication table, but you could actually, there was actually what I would think of as an architectural structure to a group. So you can actually close your eyes and visualize. And I've told my wife a number of times that, which doesn't illuminate anything, but I think amuses her, that if a group is looking like a birthday cake with several tiers and then a couple of candles sticking up on the top, that's one kind of group. Other people think of groups as a beehive with the elements buzzing around inside it. There are different ways to visualize a group, but there is an architecture to a group. And it's built just the way buildings are built out of bricks and molecules are built out of atoms. Groups are built out of certain specific types of groups that are called simple groups. So the fundamental building blocks of all finite groups, finite just means there are not infinitely many things. So it's not like the full rotation group of the sphere. There are only finitely many things in it. All finite groups are built out of simple groups as their building blocks in an explicit way and so the terminology, because Galois being French, if you've studied some French, you've probably heard in terms of verbs, you talk about the passé composé and the passé simple for a verb. So there's the composite past and the simple past. Well, so Galois took that language and called general groups, group composé, composite groups made out of these smaller things that he called group simple, or simple groups. Having worked on them for 50 years or so, I tend to think of myself as younger than I really am. I can assure you that simple does not mean easy. In any case, Galois did this work and nobody understood what he was talking about. He submitted papers to the French Academy and they were rejected or not even looked at. The first person who really understood what Galois was doing was another French mathematician of a later subsequent generation, Camille Jordan, who around 1870 wrote a beautiful book in which several hundred-page book, doing exposition of these notes, of these scribbled notes that Galois had written down, and very modestly said that what he was writing was just a commentary on Galois' work. And one of the greatest mathematicians of the first half of the 20th century, Hermann Weyl, who did a lot of work related to physics and also, of course, other mathematics, wrote the following: Galois' ideas, which for several decades remained a book with 7 seals, which you may know as a biblical reference to the or you may know from the movie The Seventh Seal. remained a book with 7 seals, but later exerted a more and more profound influence upon the whole development of mathematics, are contained in a farewell letter written to a friend on the eve of his death, which he met in a silly duel at the age of 21. Weil didn't check carefully. Actually, Galois was still just 20. His birthday was in October, and he died in May. The letter, if judged by the novelty and profundity of ideas it contains, is perhaps the most substantial piece of writing in the whole literature of mankind. Hermann Weil said this in a set of 4 public lectures he did on called Symmetry in Princeton, the early 1950s. Okay, so that's as much as I'm going to explain about what a simple group is, except to mention that Camille Jordan, besides all the other things he did, compiled the list. I mean, he did mathematical proofs that certain families of groups were, in fact, simple groups. I won't go into that. And then he compiled a list of all the simple groups that he knew. He knew several infinite families. I just mentioned the group that I mentioned before, AN, which is half of the full symmetric group, the group of all even permutations of a deck of n cards, all of those for n equals 5, 6, 7 on forever. Each of those groups is a finite simple group. Also, I'm being a little bit inaccurate here. When I say the groups SO and F of all rotations of n-dimensional space. Now, if you think of space, you probably think of space as parameterized by the real numbers, which are infinite, and the group of all rotations of 3-dimensional space or any larger dimensional real space is an infinite group. But there are finite analogs of that group. I won't try to explain, but you can replace the real number field with finite fields. That's what I'm labeling with this letter F. And if you take this rotation group for n-dimensional space over a finite field, then you get a finite simple group. And there were other examples. And this list was expanded by Leonard Eugene Dickson, who was one of the first PhDs from the University of Chicago in the late 1890s. And I can't resist telling you, I might get choked up because I tend to do this. But anyway, there's this lovely story I was told, I think, by Walter Rudin, who had known Dickson. Dickson, so at some point in his illustrious career, Dickson was given an honorary doctorate by Harvard University, and somebody from the Harvard student newspaper interviewed him and asked him and said, "This must be the proudest day of your life." And Dickson said, "No, not really." Said, "The proudest day of my life happened early in my career when I went to a math conference to give a lecture, maybe the first time, and to prepare in the break, I came into the lecture hall and I started writing the statement of my main theorem up on the blackboard and such, and finished writing it. And there was an old man sitting in the front row, and he called me over and said, 'Did you prove that theorem?' Dickson said, 'Yes, I did.' And the old man said, 'I tried for the longest time to prove that.' And the old man was Camille Jordan. I find that a very touching story. In any case, Jordan was a great mathematician and did all that work. And an immediate contemporary of Jordan in Paris was another mathematician named Émile Mathieu. And the reason it's significant to mention him is because of the word sporadic in the title of my talk. Because the very first simple groups that are called sporadic simple groups were discovered by Amy and Mathieu in the 1860s. There were 5 of them, and Mathieu actually singled out 2 of them, and the other 3 are subgroups of the 2 that Mathieu described. He gave a very careful description of the group that came to be called. So this started the tradition. You get your name, or at least your initial, on a group if you discover it. That makes it really desirable to discover a group. And so so there's a group called M12, which is a subgroup of A12, this group of all even permutations, but it's not the full group. It's much smaller, but it's a huge group. Its size is 24 times 23 times 22 times 21 times 20 times 48. Pretty big number, but much smaller than 12 factorial. And anyway, Mathieu discovered that group and another group called M24 inside the alternating group on 20. Another indication of the fact that although this all sounds very abstract and inapplicable, it turns out that, well, it's interesting. M24, Mathieu's description was not very detailed. I mean, he wrote down permutations that would generate this group, but he didn't write down a lot of details. He was very careful about M12, but not about M24. And about 40 years after Mathieu's work, a notable American group theorist, G.A. Miller, published a paper proving that M24 didn't exist. He was wrong. Apparently, he realized he was wrong shortly thereafter, because he then published another paper proving properties of M24. But it wasn't until a mathematician named Witt in the 1930s gave a really lovely description of these Mathieu groups in terms of certain geometrical systems, things called Steiner systems, which is sort of like generalizations of projective planes, that people could really clearly see that they exist. And these Steiner systems associated with these groups lead to the construction of certain things called the Golay codes by a mathematician, Golay, in the period of the late 1940s or early 1950s, and they became very important in coding theory. They were extremely good codes to use for error-correcting codes, and so they became very applicable. And almost every one of my friends, not I, but most of my friends in the group theory world have worked for the National Security Agency on coding and cryptography because of the connections between group theory and coding theory. Anyway, that was Mathieu. At the turn of the century, from the 1890s to 1900s, one of the great group theorists was an Englishman named William Burnside, who in particular in his textbook, Theory of Groups of Finite Order, written around 1900, Burnside coined the term sporadic for groups. He referred to the only known sporadic simple groups, the Mathieu groups. He referred to them as apparently sporadic because they didn't fit into, there were these infinite families that Jourdan and Dixon had written down, the alternating groups, the rotation groups, other linear groups and such that came in infinite families. And then there were these 5 cockamamie groups that didn't seem to relate to anything else except themselves. And so Burnside, with considerable insight, said that they were apparently sporadic. Just popped up here and there. And besides that coinage, Burnside was one of the first really important contributors to the effort to determine all of the finite simple groups. And this will come up later. I wanted to mention that, among other things, not one of the more important things he did, but he made a list in the appendix of his book of all the simple groups that he knew that had fewer than 1 million permutations in them. As we said, the groups get very big. They get extremely big. So he listed all the groups that he knew that had fewer than 1 million permutations. He also championed an important conjecture that a simple group, so the number of permutations in a group, it's a finite group, so the number is either even or odd. And people knew a lot of these groups that had even size, none that had odd size. And Burnside conjectured that the size of every simple group had to be an even number. That turned out to be true. Apparently, but you could also have said other things, because many years later, my thesis advisor at Yale, Walter Feit, found an old copy, I think at the University of Chicago Library, of Burnside's book with a marginal comment written in it by Leonard Eugene Dixon, who I mentioned, saying also must be divisible by 3, because all the known groups up until the time Dixon was writing it, simple groups, also had size divisible by not only by 2, but also by 3. But Dixon was wrong. One infinite family that has size not divisible by 3. But Burnside's conjecture was correct. And that brings me up to connections with the Ohio State University. So there was relatively little group theory work done between the time that Burnside died around 1927 and the late 1940s, because the Western world was busy with other things like a Great Depression and a major world war, and so people were distracted from the really important thing, which was group theory. But once the war was out of the way, people got back to being interested. You know, almost all these excellent mathematicians from this period, of course, served in the war effort during the war. And one of them was Marshall Hall, technically Marshall Hall Jr., but I've always thought of him just as Marshall Hall, who was one of the leading American mathematicians of the post-World War II era. He had a position at Yale University, but because of a terrible feud between 2 of the leading mathematicians there, he didn't feel comfortable. I could tell you this story, but I won't. So he moved to Ohio State in 1946, and he stayed at the Ohio State Math Department until 1959, when he got a position at Caltech. And during that time, when he was at Ohio State, he wrote a very influential textbook. I'll mention a few. There was Burnside's textbook, there was Marshall Hall's textbook. The next person I'm going to talk about wrote a textbook in between these 2 that was very influential. Theory of Groups in 1959. Marshall had 6 PhD students at Ohio State, and one of his mathematical grandchildren, so a student of his, so one of Marshall's students got a position at Michigan State, I believe, and had a PhD student named Frank DeManna, who came to Ohio State as a faculty member and had a very long and good career on the Ohio State faculty. And somebody I'll mention more shortly, John Thompson, who, along with my thesis advisor, Walter Feit, totally revolutionized the field of finite group theory. And as a student at the University of Chicago, John came and visited Marshall here in Columbus. And Marshall actually proposed the problem that became Thompson's PhD thesis, which was a remarkable theorem and really started the whole modern era of finite group theory. That was one big contribution Marshall made while he was still at Ohio State. And then later, while he was at Caltech some years later, Marshall got interested in this list that Burnside had put together of all the simple groups of order of size less than 1 million that Burnside knew, and started checking the numbers to see if he could rule out all the other possible sizes as sizes for a simple group. And a lot of numbers are very easy to rule out, but he hit this one number, 604,800. You probably would have guessed that one. It's a problem too. Just kidding. But he hit that number and couldn't manage to rule it out, And in fact, he began to suspect that there was another simple group that Burnside didn't know about of that size. And he began to construct it as a group, as a set of permutations of, if you deck of 100 cards, certain set of permutations on 100 things should give this group of size 604,800. I've heard Marshall give a lecture at Yale when I was a student there, and it's the only time I've ever seen anybody do this. It made me feel that this must be the way he thought. It must have been important to the way he thought about things. He actually went up to the blackboard and and he wrote every single number from 1 to 100. It must have helped him focus his thinking to actually see all those numbers sitting there right in front of him. Mathematicians usually use ... 1, 2, 3, and then figure everybody knows where the ... 98, 99, 100. No, Marshall wrote every single number, 1 to 100. On the blackboard. Did a lot of remarkable work, connection to sporadic groups, I'll get back to, because the other person who's named here, so this group that he discovered is called the Hall-Yanko group because it was more or less simultaneously discovered by a fellow named Yanko, who coincidentally was also on the faculty here at Ohio State, just for a few years, but later on. Anyway, the bottom thing, this funny looking picture was my contribution to modern art, plagiarized from Degas. I took a famous painting of Degas called L'Absinthe, of two people sitting drinking in a bar, and I sort of put John Thompson, Walter Kite into the picture. But when they did their work, they were much younger. This was a picture I took when John was, I think, 70 and Walter 72. But when they were kids of about 30 and 32, John and Walter proved Burnside's conjecture that any finite simple group has to have size an even number. There are no simple groups whose size is an odd number. And the paper filled an entire volume of the Pacific Journal of Mathematics. It was 255 pages long just to prove this one theorem. And it was sort of staggering that the proof of one mathematical theorem should require 255 pages of really difficult and mechanics. The ideas in the paper really created the whole modern field of finite group theory. Thompson, in recognition, I mean, they shared the Cole Prize in algebra for this paper, which was a very important prize in the mathematical community. Thompson got some even more remarkable awards, the Fields Medal in Mathematics, the Abel Prize in Mathematics, and of course, the crowning accomplishment of his career, an honorary PhD from Ohio State University. And if anybody wanted to have a photo of him receiving his honorary doctorate from Gordon Gee. Because of that talking, it doesn't have the numbers. think Hans died in 1991. Um, Hans Zassenhaus was in the era before the Thompson Revolution. He was considered one of the 2 or 3 most important group theorists in the world. His work was extremely important and influential. He wrote a textbook as a rather young man, having just fairly recently completing his PhD in Hamburg under Emil Artin, and inspired by the really revolutionary work in terms of the study of the structure of sort of the architecture of algebraic structures, the work done by Emmy Noether. He wrote a textbook on group theory, their book, Der Gruppentheorie, in which he acknowledges Emmy Noether as the important influence in his book. It was definitely the most important group theory textbook between Burnside's book that came out in around 1910 and Marshall Hall's book in 19. There's a class of groups that Hans began the study of, which came to be known, he didn't name them that, but came to be called Zassenhaus groups. And Walter Veit and Michio Suzuki discovered the only simple groups whose size is not divisible by the number 3, thereby disproving Dixon's marginal comment. He discovered this infinite family in the course of completing the classification of Zassenhaus groups. These so-called Suzuki groups are examples of Zassenhaus groups. And anyway, a lot of the important work in group theory in the 1950s was associated with this area that Hans originated in the late 1930s. He joined the Ohio State Math Department in 1963, remained for a long time until he retired in 1982, also retirement at the age of 70, and he remained active until his death in 19. He attracted many important group theorists as visitors, at least 1 or 2 to join the faculty, quite a few others to come as short-term visitors to Ohio State. He supervised 21 PhD students. Tell you one more story that I find very touching. There were lots of funny stories that people have told about Hans. He was the quintessential absent-minded professor, and there are lots of stories to validate his absent-mindedness. But the most beautiful story I know was told by my colleague Alan Woods, who had heard this from the widow of Emil Artin. Emil Artin had been Hans Zassenhaus's PhD supervisor in Hamburg, and Hans was studying in the late 1920s and the early 30s, which was, of course, a terrible time in Germany, time of Great Depression and a lot of poverty in the country. And apparently when Artin told his wife that he would like to invite this brilliant student of his over for dinner, his wife said, "Oh, yes, of course." And so they invited Zassenhaus to come over to their house for dinner out in the suburbs of Hamburg. And dinner was set, say, for, I don't know for what time, 6 o'clock. 6 o'clock came, no Hans. 7 o'clock, no Hans. 8 o'clock, no Hans. Finally, around 9 o'clock, Hans showed up at the Artins' house, apologizing that he had been wandering around downtown. I'm sorry, I have trouble telling these stories. Hamburg, and there were all these poor people on the street begging for money, and he started giving away his money. And he intended to save some money so they could get a cab out to the suburbs to the Artins' home, but he suddenly realized he had given away every penny he had. He didn't even have any coins to make a phone call, so he just walked all the way from downtown Hamburg to the Artens house to apologize. And getting back to, I mentioned, whoops. So I mentioned this name in the context of Marshall Hall. Marshall Hall, as I said, was one of the discoverers of what came to be called the Hall-Yanko sporadic group. The other one, as you might guess, was Yanko. Svanimir Yanko was by birth Croatian, lived for many years in Australia on the faculty at Monash University. Now, in the 1860s, Mathieu had discovered his 5 sporadic simple groups. No more sporadic simple groups were discovered in the intervening years. By the early 1960s, I imagine, I mean, it's a little before my time in the field, but I think people thought that everything was being tied up. There was a great Belgian mathematician, Jacques Tits, who had a theory of so-called BM pairs, which would have put everything together. It seemed like there was a nice package that you could tie up and say, this is the package that all the simple groups are in. And just as everybody was becoming complacent that we knew everything about simple groups, Yanko discovered a new simple group. A new sporadic simple group, the first one since Mathieu in the 1860s. So this is 1964. Yanko discovered a simple group of size 175,560. This set off, it was like the gold rush in the California gold rush or the Yukon gold rush. Suddenly, everybody got excited about the possibility, or slowly but surely people got excited. In particular, Yanko had a certain methodology for trying to find sporadic groups. And so 2 years after he found his first one, he got evidence for 2 more, which sometimes are called J2 and J3. So the first one was J sub 1, J sub 2, J sub 3. But J sub 2 also should be called HJ for Hall and Yanko, because Marshall Hall was discovering the group at exactly the same time that Yanko discovered his group from a completely different approach. Marshall Hall's approach was completely different from Yanko's. It had a lot more to do with permutation calculations, as you can imagine from somebody who writes the numbers 1 to 100 on the blackboard. And so Marshall gave a lecture at a conference on his construction of the Hall-Yanko group. And 2 people in the audience, Don Higman, who spent his career at University of Michigan, and Charlie Sims spent his career at Rutgers University, talked to each other, decided, we can discover a sporadic simple group. So they probably stayed up all night, and by the next day, they had a new sporadic simple group that came to be called, as you might guess, the Higman-Sims sporadic simple group. And that really set things off. Now it's like, wow, anybody who can do some calculations can discover a new sporadic simple group. And indeed, they started coming quickly. 13 groups between the time that Yanko discovered J1 and the end of the 1960s. 13 sporadic simple groups were discovered to add to the 5 that Mathieu had discovered. So we're now up to 18 sporadic simple groups. I mean, sporadic is just a descriptive, there's no sort of intrinsic definition. It's just, the definition is just that it's a group that is not contained in some infinite family of simple groups. So there are the alternating groups, which are an infinite family, and there are the projective special linear groups, which are an infinite family, and there are the orthogonal groups, which are an infinite family, and then there are a few more. Right now, we've made it up to 18 miscellaneous groups, some of which are sort of related to each other, but not related to any big infinite family. And so after discovering those groups, Janko was lured probably by Zassenhaus, who was already on the faculty at Ohio State. He joined the Ohio State Math Department in 1969 and brought along a recent PhD student of his, Sia Wang, who Sia stayed for many years on the faculty at Ohio State. Janko left in 1972, so he was only on the faculty for about 3 years. And Sia Wang tells me that Janko had two students at the same time. One was Sia Wang, another was Dieter Held, and he would give them problems to sort of try to find a new simple group by considering some internal structure, and he gave Sia Wang a choice of two problems that he could work on. He chose the wrong one. So Sia got a theorem and a PhD, and Dieter Held got a new simple group. So, you're miss. And another thing that Janko accomplished was that he recruited Koichiro Harada to join the math department at Ohio State. And Koichiro remained for his entire career. He joined the faculty at Ohio State in 1971 and remained until his retirement in 2006, when his wife moved back to Japan, where Harada had quite a few excellent PhD students. He had 10 PhD students in all at Ohio State. And in the 1973-74 academic year, he was a visitor at Cambridge University in England. And there was a lot of excitement at Cambridge University because just recently, independently, two mathematicians, Bob Grice of the University of Michigan and Bernd Fischer, a German mathematician, had both discovered a huge sporadic simple group, which John Conway, who was on the faculty at Cambridge, dubbed the monster sporadic simple group. And this was very exciting to study its subgroup structure. And Harada in particular studied a certain subgroup of the monster, which led to the discovery jointly with a colleague of Conway, Simon Norton, of a simple group which came to be called, of course, the Harada-Norton sporadic simple group. And Conway and Norton and three of their other friends put together this modest volume called that they call the Atlas of Finite Groups. The Atlas of Finite Groups is really a misnomer. It's really should be called the Atlas of Sporadic Simple Groups and Their Friends. It's mostly about sporadic simple groups and certain important subgroups of those sporadic simple groups. And it was producing, in particular, something called the character table of these groups. This thing spread out of those two pages, this huge collection of numbers, is the character table of the Harada-Norton sporadic simple group. The smallest space on which it acts has size 133, and the numbers get very rapidly very large in this table. And Harada tells me that he was sitting at a table, a sort of public table in the math department at Cambridge University, trying to compute what these numbers were going to be. And he had a whole bunch of equations that this set of numbers had to mutually satisfy. He was trying, and he had a list of possible numbers, and some subset of the numbers on this list had to satisfy these equations. And he was staring at the equations, and Simon Norton walked over and said, "What are you doing?" And Harada explained to him what he was trying to do, trying to find certain numbers that satisfied these equations. And Norton looked down and said, "This one, this one, this one, this one, this one, and this one." And Harada said, "How do you know?" And Norton said, "Oh." And of course, once somebody tells you the right answer, if you have an equation and you want solutions, and you can check that if somebody gives you the numbers that they satisfy the equation. And so Harada checked, and Norton was, of course, right. Norton had a remarkable brain, a very special person. But anyway, Harada did. So that's one more. I'm almost done. So at this point, once the Harada-Norton simple group was discovered, there were 25 now. The numbers had gone up from 18. My close collaborator, Richard Lyons, had discovered a group in 1970. That was the next one after the 60s, which came to be called the Lyons simple group. And so a few more were discovered. And so there were up to 25 after the Harada-Norton group. And then one more was discovered later that year by Yanko. And C.O. Wong tells me, Yanko was so happy that he discovered the first modern sporadic simple group and the last modern sporadic simple group. And he had it all bound together in a nice leather volume. There it is. He knew that the problem was finished because it had such a beauty to it. Yanko did it at the beginning and did the end. Of course, actually proving that Yanko was right, that that was the last one, is a big challenge that we're still working on. Danny Gorenstein and Richard Lyons started a project in 1982 to verify that this list of sporadic groups was complete. So there's a difference, in some sense, doing this is like getting the periodic table of the elements. I mean, the elements are the building blocks of molecules. So in that sense, they're like simple groups. I think the notion of doing things like periodic table of the elements, which was done like began with Mendeleev in the 1860s or 70s, started people thinking about classifying all things with some property. But the thing is, you can never prove, the real world is much more complicated than the world of finite groups. You can never prove that you know every single element. Somebody can always get some very rapid centrifuge or something and discover a new element, bigger, as you know. But you can actually, because mathematics has axioms and you can prove theorems based on those axioms, you can actually prove a theorem, or at least attempt to prove the theorem that says these are all the sporadic simple groups. Nobody will ever find another sporadic simple group. That's the project. In some sense, this project was completed in 2005. We're still writing this up carefully. That's the 10 volumes that we've written. Danny Gorenstein, unfortunately, tragically died in 1992, but Richard Lyons and I are continuing this project. We've produced 10 volumes so far, and we anticipate 3 more to complete the whole project. I had a near brush with mortality. Back when I was working on my PhD dissertation at Yale, I found evidence for the possible existence of a whole new infinite family of simple groups. Boy, was I excited. I was so excited that I passed up the opportunity to go to a group theory conference in Gainesville, Florida in 1972, which would have been my big chance to meet Yanko before he moved back to Europe. But in the end, what I succeeded in doing was proving that these groups' internal properties, which look very promising, still don't lead to a group. However, my consolation prize was 20 years later, The French mathematician Louis Pouch initiated the study of a class of mathematical objects called fusion systems. Every group has an associated fusion system, but not every fusion system comes from a group. So there are more fusion systems than groups. If the fusion system doesn't come from a group, it's called exotic, because the word sporadic has already been used. It's called exotic. It turns out that my non-groups are probably the only exotic simple fusion systems at the prime 2. That's my consolation prize. And just to close, the OSU Math Department, as you may know, is housed in 2 buildings with the imaginative names, the Mathematics Building and the Mathematics Tower. Always thought they deserve more interesting names, and I thought an excellent choice, given 2 of the most illustrious mathematicians to have spent lengthy careers at the Ohio State Math Department, is one of them should be named Marshall Hall, and the other should be named Zassen House. But no, suggestion has not been taken seriously. Okay, thank you very much.
Thank you very much. So I have the microphone I can pass around. Questions? Here we go.
This is not a math question, but Marshall Hall left Yale, and you said because of a conflict there between 2 different members. Was it a personal attack against him?
Happy at Princeton. As it transpired, Hilla did marry Ora's daughter, but this is just out of Jacob, out of the story in Genesis. He married the wrong daughter. He married the younger daughter, leaving the elder daughter still unmarried. And Ora could not forgive him for this. So there was this enormous hostility for years and years in the Yale Math Department, apparently, between the people who were in the Hilla faction and the people who were in the Ora faction. In fact, I went to, when the first sort of grown-up get-together in the Yale Math Department that I went to in my last year as a graduate student there was Arnold Hedlund's retirement party, and Charlie Rickert just gave a really moving tribute to Hedlund, who was saying, save the Yale Math Department by coming to become the chair of the math department when he did. And I had no idea what Rickert was referring to. But then I went to Chicago and met Felix Browder, who said, oh, I have a good story to tell you. And so he told me this story about what happened to the Yale Math Department for years, this terrible feud in the 40s and 50s between the Hilla and the Ora faction because Hilla married the wrong daughter. Dan?
The question was, when will he finish the 15th volume? 13th.
Well, it's not it's not quite as bad as it sounds, like 3 more volumes, but there's a huge amount of, there, almost the full contents of two of the 3 volumes have been written for us by our friend and colleague Gernot Schroth. And so there's really only 1 volume or a little over 1 volume that Richard and I have to complete. I'm hoping we'll complete that volume by the end of next year. I'm hoping within 2 years we'll get that next volume completed, and then there'll be, you know, just putting Gernot's work, cleaning it up, and getting that published will take another couple of years probably. That's my hope.
With the new technology and AI as a possible tool, has that facilitated any of your work, or has it been contributing to the power of AI?
I think my sister-in-law, who knows how to work whatever it's called, she put in finite simple groups or something into that, and all it did was spit back some stuff that it had plagiarized out of a few expository articles. I don't think any of that stuff at this point, I'm not predicting what will be true 25 years from now, or maybe even just 10 years from now, but at the moment, no, it's of no assistance. Computers have been of assistance. In fact, to complete his, even though Marshall Hall was an incredible hand calculator, he apparently got assistance from some English mathematician, I think it might have been Mordell, who really knew how to do some computer programming back in the 60s. It was less common than it is for mathematicians today, to help him complete the verification that the Hall-Yanko group really existed. So going back even to then, computers were already being used, and some people became incredibly gifted at writing computer software to do these calculations. Because if you're computing, the group that my friend Richard Lyons discovered, or at least he found considerable, people wrote papers that said evidence for the existence. And in fact, you got lots of information, but to prove that this thing really existed, you had to do calculations with permutations, and the smallest size permutations that the Lyons group would act on were size over 8 million. So even Marshall Hall couldn't write the numbers from 1 to 8 million on the blackboard. So Charlie Sims had to come up with some incredibly clever computer algorithms to enable computers to prove that the Lyons group existed. So proving the existence of a lot of depended on computers. Although Bob Grice, his incredible credit, was able to prove the existence of this monster, which was too big to put on a computer. So Bob did it by hand. Yeah, when Charlie Sims constructed Richard's group, Richard was a postdoc at Yale, and I was a graduate student at Yale, and I gave him a cigar with a wrapper on it saying it's a group.
We have some online questions. Let me see. Mark is asking, are there practical applications of sporadic simple groups?
Well, as I mentioned briefly, I mean, for most of the sporadic simple groups, not that I know of, for the Mathieu groups are intimately connected with these Steiner triple systems and Golay codes. And so error correcting codes have been written using these combinatorial structures, which are very, very closely tied to some of the sporadic simple groups. For the larger, Freeman Dyson, as you may know, the famous physicist, said that there ought to be an important role for the monster in the structure of the universe, but that's just wishful thinking as of now. Nobody knows for sure.
I don't know if you can see the other question. What is your opinion about the fact that the corpus of group theory is so massive? Question 2, why is mathematics so
Complex, I guess.
complex? Yep.
At at one point, when I was visiting John Thompson in Cambridge, he said to me, either we've all been very clever or we've all been very stupid. It's just, I mean, you can, it's always possible there might be a much easier way to do all the work that we're spending thousands of pages doing. So, I mean, I have no doubt that John Thompson is very clever, but notwithstanding which, there might be easier ways to do some of these things, but it's intrinsically, it's sort of almost bound to be complex to get an identification theorem which identifies something like 18 infinite families of groups together with 26 miscellaneous sporadic groups. Just to get even a complete description of these is long and complicated, and to get a classification theorem is bound to be, I think, very complicated. The inspiration for a lot of this was work by Wilhelm Killing and Élie Cartan in the 1880s and 1890s, who classified the finite dimensional semi-simple complex Lie algebras and Lie groups. So there are these infinite groups called Lie groups, but you can associate a linear structure, a so-called Lie algebra, with a Lie group. And if you can do linear algebra, that's easier than a nonlinear situation, which group theory is. And one of Hans Sassenhaus's dreams was to find a linear structure by looking at the so-called integral group rings, or looking to linearize the problem of classifying finite simple groups, but that doesn't appear to be possible. At least nobody's found any any promising approach that way. So it would be lovely to have an easier way, but maybe just intrinsically very difficult.
Do we have any other questions? If not, I'd like to thank you once again for
Thank
having
you.
an
Thank you
intriguing
so much.
meeting.